All right, well, welcome to our lecture recording for section 7.4. So, section 7.3 was our introduction to polar coordinates, and in section 7.4 we're going to continue talking about polar coordinates, and at this point our attention shifts to doing calculus with polar coordinates. So, we are getting very near the end of our course. We've got one more section after this, and then we're at the end of our material. It's kind of a shame because there's been lots of interesting things to study in this class, but I know that you all have many more interesting things to study in upcoming classes. So, let's finish this class strong. Alright, here is our outline for section 7.4. So, discussion point. One of the advantages of using polar coordinates is that for some curves, they lead to simpler equations. So here's an example. A curve that's known as a cardioid is described in polar coordinates by r equals 1 plus sine theta. Let's have a look at that. I think when we graph it, it'll be somewhat clear why it's called a cardioid. Okay. Aha. Desmos. R equals 1 plus sine, and remember we have to spell out theta. Okay, well, it looks like I'm going to need to zoom my view in, so I'll click this plus sign a few times. Okay, now that you see it, the view is kind of upside down here, but can you kind of see that this looks sort of like an upside down heart? Okay, I know we usually expect hearts to be pointy at the bottom, but you know, it's the kind of thing that you kind of have to be like, well, somebody had to decide what to call this. What does it kind of look like? Yeah, it kind of looks like a heart. Okay, so that's why it's called a cardioid. Okay, fairly straightforward equation in polar coordinates. Let's convert this over to rectangular coordinates just to see what it looks like then. Alright, now to make this conversion over to Cartesian coordinates, we'll have to use some conversion formulas that were introduced in the last section. Previously I mentioned that it would be a good idea to write them out every time you use them, and that'll help you commit them to memory just in the course of using them. So there's four main formulas that we need to use. Okay, the formulas that allow us to convert, now this would be if we were converting points, but the formulas that allow us to start with r and theta and go over to x and y are x equals r cosine theta and y equals r sine theta. Okay, so if we knew the values of r and theta, we could plug them into these formulas to get the rectangular coordinates x and y. Okay, conversely, if we know x and y, we could use these formulas: x squared plus y squared equals r squared, and tangent of theta equals y over x. If we know x and y, we could use these formulas to get r and theta. Okay, when you're just converting points, it's pretty much always these two to go from polar to rectangular, and these two to go from rectangular to polar. But when you're converting equations, you could wind up using any of them. Although I would say for equations, it's usually the top three. The bottom one doesn't come up as much when you're converting equations. Now, here is our cardioid equation, r equals 1 plus sine theta. Okay. In order to make use of these equations, I'm going to start by multiplying both sides by r. Okay, the reason I'm doing that is because, one, it gives me an r squared, which I then know how to replace with x and y, and it's also going to give me an r sine theta, and I know that r sine theta can be replaced with y. So now I can say this is x squared plus y squared, that replaces the r squared, equals, well, this will become a y, so that's pretty easy. R sine theta becomes y. But then this is a little tricky here. What do we do with an r? Well, I guess I could say r is the square root of x squared plus y squared. So we'll slip that in. Alright, so that's the polar form of the equation. This is the rectangular form. So it should be that if I type that into Desmos, I should get that same cardioid curve. Let's check and see if that works. Alright, so the polar form was graphed in red. Okay, looks like our new equation will be graphed in blue. So if we've done everything correctly, once I finish typing, the blue curve should be overlaying the red curve. SQRT gives me my square root symbol. Okay, square root of x squared plus y squared. And then we need another plus y. Aha! Hey, it worked. It worked. Okay, that is in fact the exact same curve. Okay, but notice the difference. This one is solved for the output variable r already, and it's pretty simple. This one is not solved for the output variable. It's not solved for y. So if I wanted to integrate and try to compute an area, first things first, I'd have to try to solve it for y, which could be very tricky. And even if I could figure out how to do that, which I'd have to play with that for a little while to see if I even could. But even if I could solve it for y, I'm pretty sure that solving it for y would give me something that would be much too complicated for me to figure out how to integrate. Okay, and this is to illustrate the point that for some curves, it is simpler to express them with polar coordinates, and then ultimately sometimes that makes it simpler to do things like compute areas bounded by the curve. Alright, let me head back to my outline. We did part A, we did part B, we did part C. Discussion point. Yeah, I think this is where we are. If we wanted to find the area of this cardioid, it seems likely that it would be easier to integrate the polar equation. Okay, I mean, I think I know how to integrate a sine. That seems pretty straightforward. However, this is kind of like the key however for this whole section. First, we need to consider how the area differential is different when we are using polar coordinates. So, let's consider that. We actually need to review a little formula that I think you probably learned when you took trigonometry or pre-calc, but you may not have thought about it for a while, but we're going to need it here. It's the formula for the area of a sector of a circle. Okay, so let's draw a little circle here. Okay, so there's our circle. Let's say our circle has a radius of r. Okay, and let's say we're interested in a sector of this circle whose angle, central angle, is theta. Okay, now the area of the circle, since we've just said this is a circle with a radius of r, is just pi r squared, just the basic area formula that you've known since middle school probably. Okay, but then area of the sector, what does that equal? Well, we can actually get at it through proportionality. Okay, let's do this. Let's call that A sub s for area of sector. Okay, think about it like this. If I told you that this angle was 60 degrees, 60 degrees is 1/6 of 360 degrees. So I think you would naturally expect that if this were a 60-degree angle, that the area of the sector would just be 1/6 of the area of the circle. Okay, or if I told you that this angle was 90 degrees, 90 degrees is 1/4 of 360 degrees, I think you would expect that the area of the sector would be 1/4 of the area of the circle. Okay, so I think it stands to reason that the ratio of the area of the sector to the area of the circle, which is pi r squared, would be the same as the ratio of the angle in the sector to the entire angle of the circle. But instead of calling the entire angle 360 degrees, I'm going to call it 2 pi radians. Okay, so now if I want to get a formula for the area of my sector, I can just move this pi r squared up here and say, alright, well that's theta over 2 pi times pi r squared. Do a little canceling, and I get that the area of my, looks like I'm writing the word as, a sub s. The area of my sector is 1/2 r squared theta. Okay, theta has to be in radians for this formula to be right, because we used radians there. Okay, now if you think about it, this is actually a formula you've seen before and you might remember it. Okay, but we do need it now. The area of a sector is 1/2 times the square of the radius of the circle times the central angle of the circle. Alright, now let's talk about area differentials. Let's start by talking about what we did with rectangular coordinates. So rectangular area differential. So let's say we have some curve that we have described with a rectangular equation, and we want to find its area from x equals a to x equals b. So we're interested in this area. Okay, I'm sure that you remember that the way that we approximate that area is with a rectangle that goes up to the curve. Okay, and actually we use a bunch of rectangles to overlay the area, and then we take the limit of the sums of the areas of the rectangles. But the key things to keep in mind are that the height of the rectangle is really just the y value of the curve. If we think of this as the point x comma y, then the height is whatever y is, and the width is dx. Okay, a tiny little differential in horizontal distance. Okay, and therefore my area differential, which is really just the area of one of my rectangles, is y dx. Now it's been a while since we've discussed this in this course, but earlier in the course we said that for any quantity, if we want to get the sum total of that quantity, we can integrate the differential of that quantity over whatever appropriate interval. So that means if I want to get the total area from x equals a to x equals b, I have to integrate the area differential. But the area differential, since it represents the area of one rectangle, is just a height times a width, y dx, or sometimes we say f of x dx. Okay, and that's our basic setup for an area finding integral when we're using rectangular coordinates. It's an easy setup. Basically, you just toss the function into an integral, multiply it by a differential corresponding to the input variable, and boom, you're set up and ready to go. However, when we're using polar coordinates, our input variable isn't x, it's theta, and theta doesn't measure horizontal distance. So we're going to have to take a little different approach. So let's talk about a polar area differential. So let's say I've got some polar curve. Okay, maybe it's a cardioid. Okay, but some polar curve, r equals some function of theta. And let's say here's the point r comma theta. Now in this case, if I change my input variable theta a little bit, it's not going to move me horizontally, it's actually going to sweep me radially. So if I imagine a line coming from the origin out to the point r comma theta, okay, if I advance theta just a little bit, okay, that's going to move that radial line through an angle that we can call d theta. This corresponds to the dx. Okay. Now, when I make this sweeping, okay, my area bounded by this curve is nothing like a rectangle. It's more like a piece of a pie. It may not be exactly this. The way I've drawn it, it looks exactly like it's the sector of a circle. But it may not be exactly the sector of a circle. I mean, here, this side is slightly further out than this side, okay, because r is increasing as we go up. But still, it's kind of like how the rectangle didn't have to perfectly fit the area under the curve. Okay, it could underlap a little bit or overlap a little bit, and it didn't really matter because when we take the integral, we're going to take the limit as the dx differential goes to 0, which means we're going to have a bunch of really thin rectangles, and it doesn't matter because these little gaps will disappear. Same deal here. It doesn't have to be a perfect fit, as long as it fits in a way that I believe will get better as I shrink the differential of the input variable. Okay, so I'm going to lay over a circular sector, okay, that would be a pretty good fit for the area swept out when I advance the input variable theta just a little bit. So here, my area differential isn't based on the area of a rectangle, it's based on the area of a circular sector. So instead of doing height times width, I've got to do 1/2 times radius squared, and radius is really based on whatever the function of the polar equation is, times this angle right here, d theta. Okay, this is my area differential. So if I want to compute an area using an integral of a polar curve, I need to use this as my setup. Okay, so instead of just, here y was some function of x, basically I'm just tossing that function into the integral, putting a dx next to it, and I'm ready to go. For polar coordinates, the setup is a little more involved. I have to square the function, and I have to multiply it by a 1/2, because I'm adding up circular sectors rather than rectangles. But once I get it set up, it's then just computing the integral problem. So if I go back to my outline, okay, we've done part A, we've done part B, we've done part C, and now it's time to find the area of our cardioid. Okay, so let's set this guy up. Part D. So to find the area of my cardioid, I want to integrate 1/2 r squared. So remember, in our cardioid, r was equal to 1 plus sine theta. So it's 1 plus sine theta that gets squared. and then my differential is d theta, okay, which is good. I want the variable in my differential to match the variable in whatever functions are going into the integral. Now, sometimes a tricky part with polar integrals is figuring out what the limits of integration should be. Okay, I want to compute the entire area of my cardioid, which means I need to take theta through an interval that sweeps me all the way around. Okay, now that might be 2 pi, 0 to 2 pi, but let's check on that. Okay, 0 to 2 pi. Well, whenever you put a polar curve into Desmos, it defaults to taking theta from 0 to 2 pi. Let's see what happens if we just go from 0 to pi. Okay, I'll get rid of that blue curve so it's not confusing us. Well, let me see. When theta equals 0, we would be here at 1 comma 0. And then as theta sweeps from 0 to pi, that gives me all of the cardioid that's above the x-axis. But to get the parts that are below, I need the rest of that. I need to go all the way from 0 to 2 pi. Okay, 3/2 pi? No, not enough. It's got to be 2 pi. Now you might be thinking this seems kind of obvious. 0 to 2 pi to get all the way around. The reason I'm making a big deal of it is because sometimes you don't have to go all the way to 2 pi to get all the way around. And sometimes you have to go a little bit further. So anyway, I just wanted to be sure. We'll talk about that more as we go through more examples. But for the meantime, I'm now convinced that 0 to 2 pi is the interval I wanted. Now, something that you might be wondering about is, gosh, how would I know that? How would I know that if I didn't have Desmos? Well, here's what you could do. You could try to figure out when the curve is at the origin. Actually, I'm going to modify what I just said a little bit, because a moment ago we noted that when theta equals 0, which corresponds to being on the positive x-axis or the polar axis, when theta equals 0, we're at this point right here, the point 0 comma 1. Okay, because if I plug theta into sine, I get 0, but our function is 1 plus sine theta. So what we could do is we could actually try to figure out what all angles take us to the same point. Okay, if the next possible angle that does it is 2 pi, then we know we need to go all the way to 2 pi to return to this point. The curve isn't complete until we get back. So what I'm saying is, we're going to take our function 1 plus sine theta, and we're going to set it equal to 1. Okay. Doing that is going to give me a chance to figure out when is r equal to 1. Okay. So, and if I solve this equation, I can immediately subtract 1 from both sides and get sine of theta equals 0. Now I know that sine equals 0 at pi and 2 pi. Okay, or if a particular trig function like sine that has a period of 2 pi equals some value at some angle, you can always add 2 pi to that angle and sine would still have the same value because you're essentially in the same place. So if sine of theta is equal to 0 at pi and 2 pi, then it would also be equal to 0 at 3 pi and 4 pi, or basically any increments of pi. So theta would have to equal pi k, where k is an integer. So that means that there is it means that the next place after 0, where r would equal 1, would be at pi. So at theta equals 0, r equals 1. Okay, but then at theta equals pi, r equals 1. Okay, well, but let me see here. When theta equals pi, we would be over here. So that would take me to the point, well, in rectangular coordinates. In rectangular coordinates, that would be the point -1, 0. But in polar coordinates, it's the point r comma pi, or 1 comma pi. Okay, that clearly doesn't complete the loop. Okay, so I can see I'm only halfway around there. That would help me, give me some confidence that I understand what's happening. Okay, again, we'll kind of revisit this as we go through different examples, but that's kind of a synopsis of how you analyze what's happening. Okay, all right, well, let's work out our integral. So for our integral here, 1 plus sine theta is something with two terms that's being squared. So I need to multiply that by itself. So let me see here. 1 times 1 is 1, but then it gets multiplied by a half, so I'd get a half. 1 times sine theta plus another 1 times sine theta would be 2 sine theta, but again it gets multiplied by a half, so I guess that's just 1 sine theta. And then sine theta times sine theta is sine squared theta, and again it gets multiplied by a half. Alright, now this is easy to integrate because it's just a constant. I know that when I integrate a constant, I'll just take whatever the variable of integration is and slap it next to the constant. Easy. Sine is easy to integrate. Its antiderivative is negative cosine. Easy. Sine squared. Well, for sine squared, there's a specific trig identity we need to employ to be able to integrate this. We talked about this earlier in the course. Okay, the trig identity that I have in mind, let me go ahead and rewrite this. So we've got 0 to 2 pi, we've got 1/2, we've got a sine theta, and we've got a 1/2, but right where that sine squared theta is, I'm going to drop in 1/2 minus 1/2 cosine 2 theta. So if you haven't thought about that identity for a while, that sine squared theta equals 1/2 minus 1/2 cosine 2 theta, you might want to make a note to yourself to review that. There's also an identity for cosine squared that equals 1/2 plus 1/2 cosine 2 theta. Okay, so you might want to review those if you didn't remember them. Alright, so now it's an integral from 0 to 2 pi, 1/2 plus sine theta plus, I've got to distribute this 1/2, so that'd be a 1/4 minus 1/4 cosine 2 theta d theta. I do note that I have two constant terms, so maybe I'll stick those together. So integral from 0 to 2 pi of 3/4 plus sine theta minus 1/4 cosine 2 theta d theta. Alright, now I think I'm ready to find an antiderivative. Okie dokie. That's just a constant, so its antiderivative is itself times the variable of integration. Antiderivative of sine, we've already said, is negative cosine. Here, the cosine becomes a sine. The negative sign out front won't change. However, to reverse the chain rule, I have to divide by a 2, so that'll become a 1/8. Okay, a 1/8 sine 2 theta. that needs evaluated from 0 to 2 pi. Alright, let's stick in the 2 pi. 2 pi times 3/4 would be 3 pi over 2. And let me see, when I stick 2 pi into cosine of 2 pi is 1. So I guess that'll be minus 1. When I put it in here, I would get sine of 4 pi. But sine of 4 pi is 0. Alright, and then when I stick the 0 in, putting 0 in here gives me a 0. Cosine of 0 is the same as cosine of pi, it's 1. So that's minus 1. And then putting it in here gives me a 0. Now notice, I've got a minus 1 minus another negative 1. So those actually cancel because this is subtraction. And my final answer is just 3 pi over 2. Alright, well that wasn't so bad once we got it set up. So, let's have a quick look at the theorem in the book that kind of summarizes that setup. Theorem 7.6. Now this is on page 663 of the book. It says area of a region bounded by a curve. Okay, so it says suppose f is continuous and, ooh, this is big right here, non-negative. Okay, so what that means is our r values never become negative. You remember how when r becomes negative, that causes you to hop straight through the origin and go to the opposite quadrant? That screws up integral area calculations. Okay, it wasn't really a problem with this function because 1 plus sine theta is never negative. Okay, sine can never be any less than negative 1, so 1 plus sine can't be less than 0. So our function, our polar function, can't be negative. Okay, so assume we've got a polar function that's continuous and not negative on some angle of, or some interval of angle values. Okay, now notice they're using the Greek letters alpha and beta here. So instead of a and b, they're saying I was temporarily interrupted by my 2-year-old who just arrived home and wanted to greet me. Okay. Oh, they also give us a caution that if alpha and beta are our a and b, the interval of integration, then that interval shouldn't be bigger than 0 to 2. It shouldn't be a span bigger than 2 pi. Okay, because if we go past 2 pi, we're almost certainly retracing the curve. Alright, so given all of that stuff, the area of the region bounded by the graph of, so here's where the f came from, r equals f of theta. So in the problem we just did, f of theta was 1 plus sine theta. It's whatever function of theta r is set equal to. The area of the region bounded by the graph of r equals f of theta between the angles theta equals alpha and theta equals beta equals this. Okay? And this is the setup you've got to remember. That you don't just chuck whatever formula for r you have into the integral. You take the formula for r as a function of theta, you square it, you put that in the integral, and you throw in a 1/2. Because what we're really trying to do here is we're trying to add up the areas of a bunch of little sectors. Alright, let us apply that to some examples. So, let me see. Looks like we'll start with problem 201. This is at the end of section 7.4. So, we'll advance ourselves to page, I know I typed in 677, but as you can see, that's really 669 in the book. Alright, scroll down, problem 201. For the following exercises, find the area of the described region. Okay, area enclosed by r equals 6 theta. Okay, well, before we set up our integral, let's have a little look in Desmos. we'll get rid of this, and we'll say r equals, we want 6 sine theta. Looks like I need to zoom out a little. Alright, so r equals 6 sine theta is a circle that is centered at the point 0, 3 and has a radius of 3. Now, we could have also figured that out by converting this equation over to rectangular coordinates, or we could have plotted points. Okay, Desmos was just a convenience. I will tell you, for purposes of doing your homework, I would encourage you to use Desmos to graph the function, okay, as an aid to you. You might be thinking, yeah, but we won't have Desmos when we take the test. I will tell you that for purposes of testing, I will either give you a graph to look at on the test, or I will just tell you what the interval needs to be. Okay. Once I look at the graph, I can actually kind of see something right away. Notice that the entire graph is in quadrant 1 and quadrant 2. That makes me think that all the action is happening between 0 and pi. And yes, if I reduce my interval from 0 to pi, I still have the entire circle. Check this out. If I go from pi to 2 pi, I still get that same circle. What's going on there? Well, what's going on is that as theta goes from 0 all the way around to pi, once it gets past pi, when you get down into the third quadrant, sine becomes negative. But as soon as sine becomes negative, our r value becomes negative, and that kicks me back into the first quadrant. So when I get to the third quadrant, I actually wind up just retracing what was drawn in the first quadrant. And when I get over to the fourth quadrant, again, r is negative, so it kicks me back to the second quadrant, and I'm retracing what was drawn in the second quadrant. So I actually only need to go from 0 to pi to get the entire circle this time. Now, one thing I might do is I might do, just as a check on myself, I might do like 0 to 0.9 pi. Okay, yeah, just to convince myself that, yeah, I got to go all the way to pi to get the entire circle. Now, here's another way that you could help yourself analyze this problem. So, problem 201. R equals 6 sine theta. Okay, you could say, all right, when theta equals 0, r would equal 0 because sine of 0 is 0. So we're starting at the origin. A lot of times curves complete when they get back to the origin. That's not always the case, but since I know what this circle looks like, I kind of know that it is here. Okay, once I get back to the origin, my circle would be done. So I could ask myself, when will it be at the origin again? Well, it'll be at the origin again whenever r equals 0 again. So I could put 0 in for r and solve the equation 0 equals 6 sine theta. Well, if I divide both sides by 6, 0 divided by 6 is still 0. And then I could say, oh, well, when is sine theta equal to 0? When theta is any integer increment of pi. So 0, pi, 2 pi, dot, 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 dot. Okay, what this is telling me is that this function gets back to the origin when theta equals pi. In this case, that's going to complete my curve. Now, getting back to the origin doesn't always complete the curve, because sometimes curves have multiple loops, but this curve just has one loop. So I'm now satisfied that I only need to integrate from 0 to pi to get all of the area of my circle. So let's set it up. According to our theorem, I should integrate from 0 to pi, put the 1/2 out here, and I should take whatever my function of theta that's equal to r is, and I should square that. Oh, and there's my setup. Okay, well 6 squared is 36. 36 times a half is 18. So let's put an 18 outside of our integral. And then I guess we've got a sine squared theta. But we've already talked about what to do if you need to integrate a sine squared theta. You need to pull out a trig identity that says sine squared theta. Well, that's the same thing as 1/2 minus 1/2 cosine 2 theta. Now it looks like it might be good to just distribute that 18 back through, and then I won't have any fractions. So let's say we're going to integrate from, oh, look what I did. Look at that. 0 to pi somehow became 0 to 2 pi. Let's fix that. We're going to integrate from 0 to pi, and we're integrating 9 minus 9 cosine 2 theta d theta. All right. So, antiderivative of a constant is just that constant times the variable of integration. Here, when I integrate, the cosine becomes a sine, but I also have to divide by 2. So that's minus 9/2 sine of 2 pi. And then all of this needs to be evaluated at pi and at 0. Alright, so when I plug in the pi, I get, of course, 9 pi. And when I plug pi in here, sine of 2 pi is 0. And then when I plug the 0 in, the 0 will actually zero out both terms. So my answer is 9 pi. Now, in this case, because the curve is something we know a lot about circles, we can actually kind of check our answer against other known ways of finding the area of a circle. In particular, we could check it against the formula A equals pi r squared. Remember, this is a circle whose radius that's 3, so it goes from 3 to 6. Its radius is 3. So it should be pi times 3 squared, which is 9 pi. So check. So our integration setup does seem to have given us a correct answer. But let's do something a little more complicated with it. Let's look at problem 203. Alright, so we did the area inside a circle, but now let's find the area that's below the polar axis. So that's the x-axis, below the polar axis and enclosed by r equals 2 cosine theta. Well, let's graph that. R equals 2, I already forgot what it said, 2 minus cosine theta. Okay. Alright, so remember the polar axis is the positive x-axis, so we want the area that is below the polar axis enclosed by this curve. Okay, so since the polar axis is the positive x-axis, below the polar axis would really just be quadrant 4. So let me think. Looks like 0 to 2 pi gives us the entire curve. Would 0 to pi? No, 0 to pi doesn't give us the entire curve. Okay, we need 0 to 2 pi. The fact that I'm seeing parts of the curve in all 4 quadrants is a very quick giveaway to me that I need to go all the way from 0 to 2 pi to get the full curve. But in this case, I'm not really looking for the full curve. I'm just looking for the part of it in quadrant 4. So I need to integrate from the beginning of quadrant 4, which is 3 pi over 2, to the end of quadrant 4, which is 2 pi. Alright, well, let's do this one then. Alright, so we're going to integrate from 3 pi over 2 to 2 pi. We'll put a 1/2 on the outside. And then remember our function was, oh gosh, I've already forgotten. What was it? 2 minus cosine theta. 2 minus cosine theta, but we got to square it because we're doing a polar integral. So remember, for polar area integrals, we square the function, we put a 1/2 out front. Alright, so 1/2 integral from 3 pi over 2 to 2 pi. And when I square that, 2 times 2 is 4. And then I'll have 2 times negative cosine theta twice. So minus 4 cosine theta. And then plus cosine squared theta. Now, as I mentioned before, there is a trig identity that we can apply to cosine squared, very similar to the one for sine squared. Got to be careful that I don't miscopy this. Alright, so here it is. Cosine squared theta can be replaced with 1/2 plus 1/2 cosine 2 theta. The only thing that changes is that this is a plus instead of a minus. Okay, and you know what? I think I'm going to go ahead and distribute the 1/2 back through, and I'll combine these constant terms. So 4 is 8 halves, plus 1/2 makes it 9 halves, that 1/2. But then it's multiplied by a half, so that's 9/4. So integral from 3 pi over 2 to 2 pi, 9/4. Now that 1/2 needs to distribute to the other things that are still here. So minus 2 cosine theta and plus 1/4 cosine 2 theta. Alright, now we can integrate. So the 9/4 becomes 9/4 theta. Antiderivative of cosine is sine, so minus 2 sine theta. And this becomes plus 1/8 sine 2 theta. And we've got to evaluate from 3 pi over 2 to 2 pi. Alright, when I take 2 pi and plug it in here, and that 2 cancels with the 4, and I get a 9 pi over 2. And when I put 2 pi in here, sine of 2 pi is 0. And likewise, when I put it there, I'm going to get a 0. Now, 3 pi over 2, let's stick that in here. 3 pi over 2 times 9/4 would be 27 over 8 pi. What else? 3 pi over 2's got to go into sine. Well, sine of 3 pi over 2 is negative 1. Times negative 2 makes plus 2. And then when I put 3 pi over 2 into this last piece, the 3 pi over 2 gets multiplied by 2, leaving just the 3 pi. Sine of 3 pi is 0. Alright, so I have 9 pi over 2 minus 27 pi over 8 minus 2. Well, let me see. A common denominator would have to be 8. So multiply top and bottom by 4, I would get 36 pi over 8 minus 27 pi over 8. That would be 9 pi over 8. And if I made that 2 a 16 over 8, I could say minus 16 like that. And of course, it would be fine if you got a decimal for that as well. In MyOpenMath, you'll of course need to do whatever it asks for. But if the problem doesn't say, then generally I'm okay with either an exact form or a decimal form. Alright. So let me think. That was problem 203. Let's have a look at problem 205. Enclosed by one petal of r equals 3 cosine 2 theta. Now that's kind of a weird word, a petal. What does it mean by a petal? Well, it's actually just talking about a loop. Let's have a look at this. So what was it? It was r equals 3 cosine 2 theta. You know what? This looks like a, well, actually this looks like a clover loop on a highway, kind of. Yeah, it looks a lot like that, really. But actually, this is something that has a mathematical name. This is called a rose curve. The reason it's called a rose curve is because it kind of looks like petals on a flower. And if you start increasing this number here, you can increase the number of petals. And the more you increase the number of petals, the more it starts to look kind of like a rose. I mean, you got to really use your imagination, but at any rate, this is what's known as a rose curve, and since they call it a rose, each loop is called a petal. So that's what they're talking about. So it looks like 0 to 2 pi gives us the entire curve, but the problem only asked for one petal. So now in Desmos, I can just kind of play around with it and say, alright, let's go from 0 to pi. Let's go a little smaller. Let's go from 0 to pi over 2. Well, pi over 2 like gives me half of one petal and half of another. Let's go smaller. Pi over 4. Alright, that gives me half of a petal. Well, if pi over 4 gives me half of a petal, then what if I did negative pi over 4 to 4? Aha! That gives me one full petal. So in Desmos, you can kind of screw around with it. But if you don't have Desmos, then you kind of have to go back to the idea of, let's figure out when the curve runs through the origin, because that's when the loops close. Okay, so let me switch my view back. So now we're on problem 205. The equation, the polar equation for our curve, our rose curve, is r equals 3 cosine 2 theta. Okay, so let me see. When theta equals 0, well, cosine of 0 is 1. R equals 3. Okay, so actually this thing does not start on the origin, which means we're probably not going to use that as a starting point. Let's see if we can figure out when this thing equals 0. So let's take 3 cosine 2 theta, set that equal to 0. Now anytime I'm solving a trig equation, the first thing I want to do is isolate the trig function, so anything else needs to go away. So the first thing I would do is divide by 3, and of course 0 divided by 3 is still 0. And then I'm going to have to ask myself, alright, when does cosine equal 0? Well, cosine equals 0 at pi over 2 and 3 pi over 2, which means that what's inside the cosine could equal pi over 2 or 3 pi over 2, or Well, let me see. Pi over 2 and 3 pi over 2 are pi apart. And if I add another pi, that would get me to 5 pi over 2, which is the same position as pi over 2. So I could just say pi over 2 plus any increment of pi. Okay, these are all things that if you plug them into cosine, you get 0. So 2 theta has to equal one of those things. If you divide through by 2, you get that theta equals pi over 4. Pi over 4 plus, now I divided by 2, so this would be pi over 2 times k. So pi over 4 plus any increment of pi over 2. Now I would be inclined to say then, let's just take the first two. Let's go from pi over 4 to pi over 4 plus 2. That's 3 pi over 4. But I need to remember that it's important that my curves stay positive on my interval of integration. So I got to think about, all right, if I put 3 pi over 4 in here, well, if I put 3 pi over 4 into cosine, 2 times 3 pi over 4 is 3 pi over 2. So 2 pi, 2 theta, would go from pi over 2 to 3 pi over 2. Oh, so that means I'm going to be sweeping through quadrants 2 and 3. Oh, no. Cosine's negative over there. That will not do. Okay, so I got to back it up. Okay, let's look back at Desmos. Oops, I clicked the wrong one. I didn't want to look at me. Of course, I don't mind looking at me, but that's not what you guys needed to see. There we go. So if I go from pi over 4 to 3 pi over 4, now actually, that did give me one complete loop. So that would actually work in this problem. Okay, it's negative. Okay, or my function is negative on that interval, but it's uniformly negative for the whole interval. So actually this interval would still work. Okay, but what would be better, just for the sake of consistency, is to go from negative pi over 4 to pi over 4, because then my cosine function, cosine is always positive when we're in quadrants 1 and 2. I'm sorry, 4 and 1, when we're to the right of the y-axis. Okay, my cosine function is going to stay positive on that interval. Okay, that's what we're looking for. Okay, but that other interval would have worked too. Okay, remember, it gets squared. Okay, and you might say, hey, if it gets squared, why does it matter if it's negative? The problem is when it switches between positive and negative within the interval of integration. If it's positive the whole time or negative the whole time, it would be okay. But here's what you're trying to avoid. What you're trying to avoid is going from like 0 to pi over 2. Okay, that would give you positive area here, then it would give you negative area there. Okay, but anyway, we're trying to avoid that sort of thing. It causes a discontinuity that messes up the integral. Let's do our integration. Alright, so we're going to do an integral from negative pi over 4 to pi over 4. And I want to emphasize again that for testing purposes, I'm not going to try to screw you on the interval. I'm either going to tell you what interval to use, or I'm going to give you a picture that makes it really obvious what interval to use. So don't sweat this stuff. I just kind of wanted to address how you break down these curves when you've got the right technology to do it. Without the technology, you just have to plot a bunch of points, and that's doable, but it's super tedious. Okay, so remember, our setup requires me to put a 1/2 out front, and then whatever function of theta is set equal to r, that goes in the integral. So 3 cosine 2 theta. But then we got to square it. and we're integrating with respect to theta. Alright, so when the 3 gets squared, that becomes a 9. I think I'll recombine that with the 1/2. So I'll get a 9/2 cosine squared 2 theta. Now, I'm going to have to handle that cosine squared the same way I handled it in the last problem. I got to use my trig identity, my power reduction identity. So, using that trig identity, I'm going to just keep that 9/2 where it's at, and I'm going to replace this cosine squared 2 theta with 1/2 plus 1/2 cosine. Now remember, I told you that this power reduction identity is also sometimes called a, gosh, I can't write a cosine, also sometimes called a double angle identity, because whatever angle is in cosine when it's squared always gets doubled when we apply this identity. So if it was cosine of just theta, that would be a cosine of 2 theta. But since it's cosine of 2 theta already in the squared, it becomes cosine of 4 theta. Alright, I'll go ahead and distribute that 9/2 back through. 9/2 times 1/2 is 9/4 plus 9/4 cosine 4 theta. Now I'm ready to integrate. So when I take my antiderivative, my 9/4 by itself becomes a 9/4 theta. Here I have to divide by 4, so that becomes 9/16 sine 4 theta. And we're going to evaluate at negative pi over 4 and pi over 4. Okay, well, let me look at that then. Alright, so when I plug in my pi over 4 there, I would get 9/4 times pi over 4. So let's just go ahead and call that 9 pi over 16. Plus, now when I put the pi over 4 in here, it gets multiplied by a 4. So sine of pi is 0. Alright, now let's put in the negative pi over 4. Negative pi over 4 times 9 over 4 is negative 9 pi over 16. And we wind up getting another 0 for that second term. So I'm subtracting a negative, so I guess I'm really adding. So that'll be 18 pi over 16, or 9 pi over 8. Boom! That's our answer. Alright, so we've done several examples of integration to get an area, and I actually want to do one more, just because, yeah, this polar stuff's a little unusual, and there's some different scenarios that I want to kind of give you guys an idea of how to handle. So we've talked about finding the entire area bounded by a curve. We've talked about finding the area of just one loop, or the area in just one sector, just one quadrant. Okay, but here's one more thing that you'll see. So what did I say on the outline? 201, 203, 205, did them all. 211. 211. Let's look at 211. Burp, burp, burp. There it is. Okay, we're still finding areas. We're finding the common interior of two curves. R equals 6 sine theta and R equals 3. Well, let us bop right over to Desmos and see if we can figure out what that looks like. R equals 6 sine theta. Alright, we looked at that one earlier. That's a circle centered at the point 0, 3. The other curve they gave us was R equals 3. R equals a constant in polar coordinates, gives you a circle centered at the origin with that constant as its radius. Our problem is to find the common interior. So basically, it's this football-shaped area that's under the black curve but above the blue curve. How are we going to find that? Well, the key is going to lie in finding this point, their first intersection, and this point, their second intersection. How are we going to find those intersections? Well, it's actually the same way we always find the intersections of functions. We set them equal to each other. If we can figure out what those angles are, we can break this problem down and handle it. So, let's do that. Alright, so problem 211, they gave us r equals 6 sine theta and r equals 3. Let's set those equal to each other. So 6 sine theta equals 3. Now remember, when we are solving a trig equation, we first want to isolate the trig function. So I'm going to start by dividing by 6. So sine theta equals 1/2. Okay, well, let me see. I know that sine of theta equals 1/2 when theta equals pi over 6. Now, if you don't remember that, you could go to your calculator. Make sure your calculator is in radian mode. So let me see there. I gotta look. Yep, mine's in radian mode. And you could say, hey, calculator, what is sine inverse of 1/2? 0.5235. Oh, that's pi over 6 in decimal form. How do I figure out what fraction of pi that is? I have to take that number and divide by pi. Okay, 0.166666, that's 1/6. Okay, and if you're not sure what fraction that is, I mean, you could actually let the calculator figure it out for you using this little fraction to decimal command. Yeah, it's 1/6. Alright, so this is pi over 6. Okay, but keep in mind that there's always two solutions at least. Okay, pi over 6 would be one solution, but you've got to think, alright, so sine was equal to 1/2, that's a positive number. There's two quadrants where sine is positive, quadrant 1 and quadrant 2. Sine is positive whenever we're above the x-axis. Okay, what that means is, here's pi over 6. It's about 30 degrees. If I go over to the other quadrant where sine is positive and draw an angle that makes the same angle with the x-axis, that's going to have the same sine value. So now I got to think, alright, that's pi over 6 measured back from pi. Oh, that's 5 pi over 6. Okay, so those are two angles, and we knew we were looking for two, right? I mean, that was kind of obvious in the picture. Okay, we knew we needed an angle in quadrant 1 for one intersection and a corresponding angle in quadrant 2 for the other intersection. So that makes sense. Well, now we have the two angles. Okay, we could get the r values, but we really don't need those. The angles give me an interval of integration. Okay, but here's the other thing. Let me add in a little line here. Since I know that the angle is pi over 6, if I type tangent of pi over 6, tangent of pi over 6 is the slope that corresponds to that angle. So if I do y equals tangent of pi over 6x, that gives me a line through the origin that has the right slope to run right through this intersection point. Okay, now, and you know what, I'm gonna throw in a little restriction here. Okay, I only want x to go from 0 to 0 to 3 would be good. It'd be far enough. Oh, I got to do 0 is less than x is less than 3. There we go. Okay, that's far enough to get me out there. Alright, so now I can see that if I integrate from pi over 6 to 5 pi over 6, let's just copy that, throw in a 5 there, and let's tell it to go from negative 3 to 0. There we go. Now I can see that if I integrate from pi over 6 to 5 pi over 6, that will give me most of the area that's enclosed by these two circles. But it actually won't give me all of it. It leaves out these little wedge-shaped areas on the sides. Okay. I actually am going to have to do two integrals. Okay, for the area between the red line and the blue line, the polar curve that's giving me the outer boundary is the black curve, r equals 3. But for this little area, this little wedge-shaped area in here, where we're going from 0 up to pi over 6, for that, the polar curve that's giving me my outer boundary is actually the blue curve. So, I've got to do two integrals. Alright, so I'm going to set up two integrals. One for the big area that's bounded by the black curve, and one for the little area that's bounded by the blue curve. Now I know there's two of those little areas, but I can see they're the same, so I'll just do one integral for that and double it. So my area would be an integral from pi over 6 to 5 pi over 6. We'll put a 1/2 out front. Now remember, my black curve was r equals 3, so it's 3 that gets squared. Oh, this is going to be a very simple integral. But that's not all of the area. Now I need two integrals that give me the little wedge area. So I'm going to do 1/2 integral from 0 to pi over 6. That'll be the right wedge, and I'm doubling it. Now here it was 6 sine theta, and we're squaring that. Alright, this should give me the total area that's enclosed by these two circles. Let's work it out. 3 squared is 9, times 1/2, that's 9 halves. So, integral from pi over 6 to 5 pi over 6, 9 halves d theta. Now here I can see I got a little cancellation going, and I'm going to have an integral from 0 to pi over 6 of 36 sine squared theta d theta. Okay, now that becomes 9 halves theta. So 9 halves theta evaluated from pi over 6 to 5 pi over 6. Over here in my integral from 0 to pi over 6, I've got to replace that sine squared theta with 1/2 minus 1/2 cosine 2 theta. But then when I redistribute that 36, it's going to look like 18 minus 18 cosine 2 theta d theta. Alright, so let me see. 5 pi over 6 times 9 pi over 2, that's 45 pi over 12. Minus pi over 6 times 9 pi over 2. Let me see, that'd be 9 pi over 12. Plus, let me see, I'm going to have an 18 theta minus a 9 sine 2 theta evaluated from 0 to pi over 6. And let me see, when I put the pi over 6 into there, into the 18 theta, that's going to be a 3 pi. Alright, so let's slam these together. That'd be, you know what, that's 36 pi over 12, which is 3 pi. Okay, plus pi over 6 times 18, well that's a 3 pi. And when I stick pi over 6 in here, it gets multiplied by 2. So that's really sine of pi over 3. Sine of pi over 3 is square root of 3 over 2. So that would be minus 9 square root of 3 over 2 minus, now when I put the 0 in, I'm just going to get zeros. Okay, so 3 pi plus 3 pi makes 6 pi. 6 pi minus this fraction. So my area is 6 pi minus 9 square root 3 over 2. Let's make that 12 pi over 2. So the area is 12 pi minus 9 square root 3 all divided by 2. And again, decimal would be fine for that unless the problem specifically says otherwise. Alright, that's enough about area, but there's a whole other topic in this section. We are now going to talk about doing integrals with polar curves to get arc lengths. But before we can do that, we've actually got to tie back to something we talked about at the beginning of this chapter, parametric equations. Alright, so coming back to our outline, we're on the second page of our section 7.4 outline. We're going to look at a type of polar curve that we haven't discussed yet, or at least I haven't discussed in any of the lectures. It's a polar curve that gives us a spiral. So, the equation of a spiral is given by a rather simple polar equation, r equals theta squared. Let's look at this in Desmos. Yeah, get rid of all this stuff. R equals theta to a power of 2. Okay, it looks like I'm going to have to zoom out. Alright, if I zoom out enough, you can see why we call this curve a spiral. Okay, not any particular special spiral. If you don't put the square on it, it's an even simpler curve. Okay, if you don't put the square on it, now I got to zoom back in. Boom, 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 boom. If you don't put the square on it, then you get what's called an Archimedean spiral. Okay, named after the famous Greek mathematician and scientist and engineer Archimedes. Okay, but I like this one a little better for the examples I'm going to do. So this is, since I squared the theta, it just makes it swirl out farther sooner. But it's still a spiral. Alright, now how do we get parametric equations for that? So a little bit ago, we reviewed some conversion formulas. I'll write them again, because if you don't have these yet memorized, I would want to encourage you just one more time to make it a point to get that done. And I would say get that done by writing them every time you use them. So remember, we had x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and then tan theta equals y over x. Okay, it turns out that if you know these conversion formulas, it's actually really easy to parameterize a polar curve. Here's my polar curve. R equals theta squared. We'll call this polar form. Okay, to parameterize it, all I have to do is combine the polar equation with these two conversion formulas. Okay, r equals theta squared, So I'm going to sub theta in for r in these two formulas. That gives me x equals theta squared cosine theta, and y equals theta squared sine theta. Those two equations together give me my parametric form, because now I've written both x and y as functions of just one other variable. Let's enter that into Desmos just to see that it gives us the same curve. Alright, so remember, for parametric we have to enter it like it's a point, and we have to use t instead of theta. Alright, so t squared cosine t, comma, t squared sine t. Okay. Now, t is only going from 0 to 1, but since t is really theta, it looks like we need to let t go from 0 to 12 pi. And if we do that, yes, my blue parametric curve perfectly overlays my green polar curve, because these parametric equations are equivalent to this polar equation. Okay, now why is that useful? Well, it's useful because I already know how to do some things with parametric equations that I haven't yet talked about how to do with polar equations. In particular, I know how to do things like find slopes of tangent lines for parametric equations and arc lengths for parametric equations. So, since it's so easy to convert polar to parametric, we can leverage what we know about parametric to figure out some stuff for polar. Let's head back to our outline. Alright, so we graphed the equation in Desmos, we converted it to parametric form, we graphed the parametric equations in Desmos, but now let's find the slope of our spiral at theta equals 3 pi over 2. So, I guess this was part B here. Parts A and C were just graphing in Desmos. But now in part D, we want to find a slope. Slope is always dy dx, rise over run. The variable measuring rise, variable measuring run, y and x. I always need dy dx for a slope, unless my axes are something other than x and y. But for polar and parametric forms, my axes are still really x and y axes. Now, for parametric equations, we said we could do that as dy dt over dx dt, or if the parameter is theta instead of t, then it could be dy d theta over dx d theta. Here we're pretty much using t and theta interchangeably. So, there's my x equation. Let's compute dx d theta. Well, my x equation is really a product, theta squared times cosine squared. So to find its derivative with respect to theta, I'm going to have to use the product rule. The product rule that you all learned in Calc 1 says that to take the derivative of a product, I first take the derivative of the first factor in the product, and I leave the other factor alone. But then I write a plus sign, and this time I leave the first factor alone, and I take the derivative of the second factor. And I'm going to have to do something similar to get my dy d theta. My dy d theta would be, again, applying my product rule. It would be 2 theta sine theta plus theta squared cosine theta. So, according to the formula that we learned for parametric equations back in section 7.2, I've got to divide this one by that one to get a slope formula for dy dx. Alright, so dy dx equals 2 theta sine theta plus theta squared cosine theta divided by 2 theta cosine theta minus, because of the negative sign, minus theta squared sine theta. So now I have a formula that I can use to find the slope of the tangent line of the spiral at at theta equals pi over 2, or 3 pi over 2. So I'm going to take dy dx. I'm going to plug in theta equals 3 pi over 2. Now sine of 3 pi over 2 is negative 1. So I've got 3 pi over 2 times negative 1. That's going to be negative 3 pi. Cosine of 3 pi over 2 is 0. So that means this term is 0. And then over here, sine of 3 pi over 2 is negative 1, but there's already a negative, so that gets canceled. But I also have a 3 pi over 2 squared, so that's a 9 pi squared over 4. Alright, so negative 3 pi times, I got to flip that over, 4 over 9 pi squared. So cancel a pi, cancel the 9, there's still a 3 down there. So I guess that's negative 4 over 3 pi. Okay, now let me look back at the graph. That's saying the slope of the tangent line at 3 pi over 2 is negative. Well, let's zoom in. Okay, here's my spiral. As theta goes from 0 to pi over 2 to pi to 3 pi over 2, I can see this point here on the curve corresponds to theta equals 3 pi over 2. And it does look like the tangent line would have a negative slope. Now if I really want to test it, I could put in the tangent line. So for the tangent line, I would have to go y minus the y value of that point. What's the y value of that point? Well, the y value of that point is r sine theta. What's the r value of that point? Well, r is theta squared, so that would be 3 pi over 2 squared times the sine of 3 pi over 2. Okay, that's my y value. So y minus the y value of the point equals the slope. So that was negative 4 over 3 pi times x minus the x value of the point. How do I get the x value of the point? Well, that would be r cosine theta. So it's going to be just like this, only with a cosine. I accidentally deleted it. There, come back. I'm glad there was an undo button. I wouldn't have been... Hey, that's not funny. I'm not clicking that X. Alright, there we go. Anyway, there's my tangent line. Looks good. If I want to, I could zoom in on that point, just so I can convince myself that, yeah, the curve and the line, they're kind of blurring together as I zoom in, which is what's supposed to happen with a tangent line. Alright, enough of that. Let's go back to the outline. Okay, graphing the tangent line wasn't a required part. I just did it as kind of a visual check. Alright, So now I want to do an arc length on my spiral. And for that, I'm going to use the arc length differential for parametric equations. So we learned about this back in section 7.2. It was on page 635. Okay, so let's actually have a quick look at that. I always have to type in a page number that's 8 ahead of the page I want. I think I went by it. I think I typed in the wrong... Oh, there it is. I just scrolled the wrong way. Okay, so here's what we learned back in section 7.2. Okay, you can kind of ignore the integral for the moment because I just want to focus on the differential for the arc length that we put into the integral. For that differential, assuming I've got parametric equations where x and y are both functions of t, I take dx dt and I square it. I take dy dt and I square it. I add those together and put them in a square root, and that's my arc length differential. Well, as it happens, I've already computed dx d theta and dy d theta, so I just need to square those things and I'll have my arc length differential. Well, square them, add them together, and put them in a square root. So it looks like I'll call this ds, s for arc length. This is the arc length differential. My arc length differential is the square root of dx d theta squared. So 2 theta cosine theta plus theta squared. Well, it's really minus theta squared sine theta squared plus dy d theta squared. So that'd be 2 theta sine theta plus theta squared cosine theta squared. All of that's under the square root, but then outside of the square root we have the d theta rather than a dt. Okay. Now I know what you are probably thinking, if you're thinking about this very hard at all. You're thinking, good golly, that looks like that's going to be a mess under a square root. How are we going to integrate that? Well, I have some really good news. Those sines and cosines that are always there when we parameterize a polar curve give us some pretty nice cancellations. And this actually knocks down to a nice new formula, which we'll look at after we finish this example. Okay, so ds equals, I'm going to stretch this over 2 lines because it's going to take a lot of space to write it out. 2 theta cosine theta gets multiplied by itself, so I get a 4 theta squared cosine squared theta. But it also gets multiplied with negative theta squared sine theta, and that happens twice, so that's going to be a minus 4 theta cubed cosine theta sine theta. And then finally this term gets multiplied by itself, so I get a plus theta to the 4 sine squared theta. Now all of that is just from squaring that first term. But let's go ahead and square the second term. So the 2 theta sine theta becomes a 4 theta squared sine squared theta. And then 2 theta sine theta gets multiplied by theta squared cosine theta twice. So I get a plus 4 theta cubed cosine theta sine. Whoa, isn't that nice? Boom, boom, those are going to cancel. And also this thing gets multiplied by itself, so theta to the 4 cosine squared theta. Now, here I'm going to factor out that 4 theta squared. So ds equals square root of 4 theta squared times cosine squared plus sine squared theta plus theta to the 4 can be factored out here times sine squared theta plus cosine squared theta. All of that is under my square root. And you probably remember that cosine squared theta plus sine squared theta equals 1. So this goes to 1, that goes to 1. My arc length differential is just, I'm going to switch up the order here. It's just the square root of theta to the 4 plus 4 theta squared d theta. Now that is actually something that we'll be able to put into an integral and work out. We actually had some ones pretty similar to that when we were doing parametric arc lengths. That is completely doable. But before I go any further, here's what I want you to see. Remember, our original function was r equals theta squared. This is the square of that. Theta squared, and 4 theta squared is the square of 2 theta. 2 theta is just what you would get if you took the derivative of r with respect to theta. And it turns out that when you parameterize a polar curve and apply the integral formula for parametric equations, you always get all the sines and cosines to eventually knock themselves out, and the arc length differential that you're always left with is just the original polar equation, whatever was set equal to r, squared, plus its derivative with respect to theta squared. That's a formula that's worth knowing, so you don't have to do all this stuff every time. Okay, and that's actually captured in a formula in the book. Let's look at that formula real quick. What's the outline say here? The outline says that is on page 667. So I gotta go to page 675. Arc length and polar curves. That looks like what we want. Aha. So here it is right here. The setup is basically whatever r is as a function of theta squared plus whatever its derivative with respect to theta is squared, added together, put inside a square root, you integrate that, you've got yourself an arc length. Okay, well, let's go back and apply that. So what the heck were we even doing? We did part E, we found our arc length differential, but now let's finish it out. Let's find the length of our spiral from theta equals 0 to theta equals 4 pi. Alright, so part F. We're going to find our arc length, and we're going to find it by integrating our arc length differential from 0 to 4 pi. And here's our arc length differential right here. So we really want to integrate from 0 to 4 pi the square root of theta to the 4 plus 4 theta squared. Let me clean that up just a little bit. Yeah, that's an exponent. Now you might remember from previous examples that what we do is we factor out a theta squared. So let's see what that looks like. Theta squared times theta squared plus 4 d theta, and then we split the square root so that this theta squared just becomes a theta. So theta times theta squared plus 4, and now we can do some u substitution. we'll let u be theta squared plus 4. So then du would be 2 theta d theta. Looks like I've got to bring a 1/2 over. So 1/2 du equals theta d theta. So this becomes, let me see, a 1/2 times the square root of u du. But you know what? I went from theta to u, so I've got to convert these limits of integration as well. Looks like when theta is 0, u would be 4. And when theta is 4 pi, u would be 4 pi squared. That's 16 pi squared plus 4. Alright, well that's fairly easy to integrate. The u to the 1/2 becomes u to the 3/2, and I multiply by a 2/3. So that becomes 1/2 times 2/3 is 1/3. 1/3 u to the 3/2 evaluated from 4 to 16 pi squared plus 4. Let's get a decimal for that. So that's going to be 1/3 16 pi squared plus 4. I really want a decimal this time because I want to get a sense of whether or not it even seems right. Alright, now 4 to the 3/2 is 8. So I guess that's plus 8/3. Alright, so I punched that into my calculator, and my calculator is saying that that is approximately 684 and some change, but I'll just round it off. Round it off to approximately 684. Now, does that seem reasonable? Let's go back over to Desmos. I think we're going to have to zoom way out. Okay, 0 to 4 pi would be 2 complete turns around the curve. So there's one. Boom, there's the other one. Oh, yeah, well look, we're out 600 or 150 units from the origin there. So yeah, I can definitely see 150 back to, I mean that's just a straight line between these 2 points is 250 about. But you know, we took the long way. So yeah, I mean 684 seems completely reasonable to me. You know, now that I've looked at the graph. All right, let's do one more like this. Let's do one out of the book as an arc length problem, just to kind of go through top to bottom fairly quickly. How do we set up an arc length integral for polar coordinates? All right, so what's my last example here? Problem 219. Okay, so problem 219. So, oops, I went too far. I want to go to like 677. Yeah, that's where it is. Alright, so for the following exercises, find the length of the curve over the given interval. Our curve is r equals e to the 3 theta on the interval from 0 to 2. Wonder what that looks like. Let's see. Get rid of u, get rid of u, get rid of u. R equals e to the 3 theta from 0 to 2. Looks like I'm going to have to zoom out. Okay. You know, I think this is just another spiral, but e to the 3 theta grows faster than theta squared. Let me see. What if we went farther? What if we went to like 4 pi and then kept going out? Yeah, have to go pretty far, but it does look like it eventually turns. Yeah, that is definitely a wide-ranging spiral. Alright, well we're really just looking at it from theta goes from 0 to 2. Okay, so we want to find this arc length. Got it. Alright, back to the paper. Alright, so this was problem 219. R equals e to the 3 theta. We're finding arc length, and theta goes between 0 and 2. Alright, so to use our arc length setup, to use our arc length setup here, we're going to need dr d theta. Well, that's pretty easy to take a derivative of. We just kick down a 3. So 3 e to the 3 theta. Now, we're going to square both of these things. Okay, the formula for r and the formula for dr d theta, we're going to square those things, and we're going to put them inside a square root and add them together, and that'll be our arc length differential. So we're going to integrate. This will give us our arc length from 0 to 2, square root. We're going to take an e to the 3 theta, we're going to square that, and we're going to take a 3 e to the 3 theta, we're going to square that, and we're going to take a square root of that sum and integrate with respect to theta. Okay, so I've got an e to the 3 theta squared. Now I could simplify that, but I actually kind of like it as e to the 3 theta squared, because in a moment I'm going to factor that out of both of these terms. Let's go ahead and square this 3. Let's make that a 9, but then still an e to the 3 theta squared. Alright, so I've got e to the 3 theta in both of these terms. They're added together. Let's factor that e to the 3 theta out. So I've got square root of e to the 3 theta squared times 1 plus 9. Alright. Well, I can split my square root here. Okay, on the left of the split, the square root will cancel the square, and I'll just have e to the 3 theta. E to the 3 theta. And over here, I guess I have square root of 10. Well, square root of 10 is a constant. That's an easy thing. Okay, I can really just focus on integrating this part, and the constant will come along for the ride. Let me see, when I integrate e to the 3 theta, I'm going to divide by 3. I'm already multiplied by square root of 10. So let's say that's going to be square root of 10 over 3. E to the 3 theta, evaluated from 0 to 2. So that's going to be e to the 6th times square root of 10 over 3 minus square root of 10 over 3, because e to the 0 is 1. And again, let's get a decimal for that. So let me consult my magical calculator here. I don't know why I think it's magical. I guess because being able to compute something like that still feels a little bit magical to me without spending all day on it. I know, that's a little naive, right? Or a little 1982-ish. Still impresses me though. Alright, so e to the 6th times the square root of 10 divided by 3 minus square root of 10 divided by 3. Alright, so about 424. Let's go back and have a look at our picture in Desmos. Yeah, I would say it looks like I'm going from 0 up to this point, and I can see that's the height is almost 400, and I'm going horizontally too. So yeah, it seems completely feasible to me that my arc length would be a little over 400. Alright, well, that's all that I wanted to do in section 7.4. So here's a couple of homework problems for this section, 206 and 220 out of the book. And of course, there's homework in MyOpenMath as well. So I hope you all have a good time working on that. And if you do get stumped by anything, please reach out to me. Oh, I'm almost forgetting. I'm almost forgetting to always say goodbye to you, my friends, face to face. So, I hope everybody is still well, staying safe. It's been cold lately, but it's warming back up, so I think maybe I'll go outside and play with my kids for a little bit this evening. Take care, everyone. Bye.